Draw a symmetric convex blob on graph paper, centered at the origin. How large can it get while still missing every lattice point except the one in the middle? Quite large, in fact. A circle can do it, so can a square, so can a much rounder shape. But all of these stay below the same number. Once the area climbs past 4, the grid wins. Here is the exact statement. If K is convex, centrally symmetric, and has area bigger than 4, then K contains a non-zero lattice point. The proof starts by shrinking the body by a factor of 2. Call the smaller copy K over 2. Areas scale by the square, so area bigger than 4 becomes area bigger than 1, and 1 is exactly the area of one lattice cell. Now cut K over 2 by the unit grid. Every piece sits in some lattice cell. Translate each piece by an integer vector until all of them land inside one chosen unit square. Nothing has changed except position. We have repacked the same set into a single cell. But that square has area 1, while the translated copy of K over 2 still has area bigger than 1. So inside that one square, the translated pieces cannot stay disjoint. Somewhere in that overlap, two different pieces cover the same point. Pick one point X from the first overlapping piece and one point Y from the second. After translation, they land on the same point. So before translation, X and Y differed by an integer vector. And because the points were distinct, that vector is not 0. It is a non-zero lattice vector. We still need to check that this vector X minus Y actually lies in K. That's the next and final step. Now we have a non-zero lattice vector, but we still need it to lie in K. Since Y lies in K over 2, central symmetry puts minus Y there too. Since X and minus Y both lie in K over 2 and the set is convex, the whole segment between them stays inside. In particular, its midpoint lies inside. That midpoint is X minus Y over 2. Doubling it puts X minus Y inside K. And remember, we chose X and Y precisely so that X minus Y was a non-zero lattice vector. So X minus Y is a non-zero point of the integer lattice, and it sits inside K. That is exactly what the theorem promised. The proof is complete. The same cut and translate argument works for any lattice in the plane. Only the fundamental cell changes. The unit square is replaced by one fundamental parallelogram, one basic cell whose translates tile the plane. If that cell has area A, then every convex centrally symmetric K with area bigger than 4A contains a non-zero lattice point of that lattice. So why does this simple area bound matter? It unlocks several classical theorems. First, every prime P congruent to 1 modulo 4 is a sum of two squares. A short pigeonhole plus Minkowski's theorem settles it. Second, given real numbers alpha 1 through alpha n, there are integers q that simultaneously make every q alpha I close to an integer. That is Dirichlet's simultaneous approximation theorem, also a direct application. And third, Lagrange's four-square theorem. Every positive integer is a sum of 4 squares. That one falls out of a 4-dimensional version of the same argument. All three fall out of this one area argument. Each one is a topic for an upcoming video. So that is the picture behind Minkowski's theorem in the plane. Shrink the body, repack it into one cell, force an overlap, extract a lattice vector, then use symmetry and convexity to bring that vector back into the original shape.